Before we begin, please subscribe to In the Beginning, so you never miss the forgotten engineering and survival techniques that really shaped history. For the first minute, imagine, if you will, a secretive research facility deep in Eastern Europe or the northern United States. Winter winds are howling outside, temperatures dropping well below freezing, and sensitive equipment, fuel, and, of course, personnel needing reliable protection from the cold. Conventional insulation often failed under these circumstances, and resources were, honestly, quite scarce. Engineers and scientists had to innovate. The solution they documented in schematics and blueprints was simple, elegant, and frankly, astonishingly effective. A layered insulation system that trapped heat with minimal bulk, using materials almost anyone could access. This is the story of that lost Cold War insulator, and how its principles can be applied today. The lost Cold War insulator worked by combining layers of natural and synthetic materials to trap air efficiently. Blueprints from the 1950s and 60s reveal a repeating pattern. Thin sheets of insulating fibre alternated with reflective layers, all contained within a rigid frame or cavity. The designers understood that air is the primary barrier to heat transfer, and that moisture drastically reduces effectiveness. By layering materials that maintain structure while reflecting radiant heat, they created a system that maximized thermal retention without relying on heavy, expensive materials. This approach allowed facilities to maintain operational temperatures in rooms, vehicles or shelters even when external conditions were, well, extremely harsh. Modern enthusiasts can replicate the principle by layering fibrous insulation, such as cotton, wool or synthetic batting, with reflective surfaces like foil or resin-coated boards. The goal, really, is to trap air in multiple undisturbed pockets while reflecting heat inward. The construction of the insulator was surprisingly practical. Engineers often used alternating sheets of fiberglass or mineral wool with aluminum foil or metallic-coated paper. The foil layers didn't generate heat. Instead, they reflected infrared radiation back toward the interior, reducing loss to the cold exterior. Mineral or fiberglass layers maintained the air pockets and prevented collapse under pressure. Some blueprints even specify spacing supports such as thin wooden battens or wire grids to prevent the layers from compacting. This combination allowed for a flexible, lightweight and durable thermal barrier, suitable for walls, floors, ceilings, and even portable enclosures. For modern use, you could achieve a similar effect with batting or foam panels interleaved with reflective emergency blankets or foil sheets, secured lightly to preserve the air gap. The Cold War engineers were meticulous about moisture control because they understood it destroys insulation efficiency. Some schematics detail vents, breathable membranes, and drainage channels incorporated into the assembly. These features ensured that condensation or snow melt wouldn't collapse the insulating layers or conduct cold directly into the structure. In practical terms, if you're applying this method to a cabin, shed, or temporary shelter, always pair insulation layers with moisture barriers and drainage where possible. The principle is simple. Air traps heat, but water displaces it. Maintaining dry pockets is as important as choosing the right material. Another reason the lost insulator worked so well was its modularity and adaptability. Engineers designed panels that could be removed, repaired, or adjusted depending on conditions. If a layer became compressed or damp, it could be replaced without rebuilding the entire system. Soldiers, lab technicians, and survivalists alike could adapt the same principles to personal gear, such as insulated sleeping mats, jackets, or field shelters. A modern adaptation might include layering foam mats, batting, and reflective foil inside a sleeping bag liner or inside walls of a temporary cabin. The design is inherently scalable, whether protecting a single person, a vehicle, or an entire structure. The efficiency of this technique lies in understanding the interplay between air radiation and structural support. Ordinary insulation relies on thickness alone, which is heavy and honestly prone to failure under compression. The Cold War insulator relied on multiple thin layers, each supporting air pockets and reflecting heat, achieving more warmth with less bulk. Well, it's a principle that, survives in modern passive heating designs, ultralight backpacking, insulation, and even some spacecraft shielding. The lesson here is clear: strategic layering and reflective management of heat can quite often outperform brute force insulation. Applying this knowledge today is honestly pretty straightforward for anyone interested in survival, camping, or even historical experimentation. You just gather lightweight insulating fibers such as wool, cotton batting, or foam sheets. Then layer them with reflective surfaces like foil blankets or metallic-coated paper. It's important to maintain light spacing between layers to preserve those crucial air pockets. If you're applying this to walls or floors, consider a rigid or semi-rigid frame to prevent collapse. Moisture control is essential too. Vents, breathable membranes or drainage channels will help maintain effectiveness. And for personal gear, this technique can really transform a sleeping bag, insulated jacket, or field shelter into a microclimate that retains heat, even in wet, windy, or freezing conditions. The lost Cold War insulator, you see, teaches us a broader lesson about historical ingenuity. Engineers didn't rely on exotic materials or complicated machines. They simply observed natural principles, experimented with layers, airflow and reflection, and documented a solution that could be replicated decades later. It's a method really grounded in physics, resourcefulness, and practical problem-solving. By studying these blueprints and adapting them to modern use, we can recover a piece of history while gaining a highly effective survival tool. If you found this guide valuable, do consider subscribing to In the Beginning and sharing this video with fellow history enthusiasts and survivalists. Preserving forgotten engineering techniques ensures that the ingenuity of the past, continues to inform practical solutions today.